Okay, last time we talked about how we can put an address on the electrons in an atom, and there were three different pieces of information that we needed to include on our address, starting with the energy level, then the sublevel, then the orbitals. And what we're going to talk about today are the rules that you need to know to be able to write down those addresses for electrons. And I compare this again to an envelope. If you're going to write out an address on an envelope, you have to know where the different pieces of information go and how to write them out. Otherwise, your envelope won't necessarily get where it's going. So again, just like an envelope, there are some rules to writing down the different pieces of information and to how we formalize that address for the electrons. So, our big idea for today, how are the electrons arranged in atoms? We're still kind of going off of what we talked about last time. But there are three rules that control how we write down those addresses for the electrons. Rule number one is called the Elfbow Principle. And this principle says that electrons will enter the lowest possible energy levels first. So if you can imagine electrons kind of filing into an atom one by one and looking for a place to sit, they're going to choose the lowest possible energy levels. The seats that are the closest to the nucleus are going to go first. So electrons enter the lowest possible energy levels first. Within an energy level, though, there's also an order. So the S sublevel will fill up first. Then if there are more electrons, the P sublevel will fill. Then if there are more electrons, the D sublevel, and then the F. So lowest possible energy levels first, and then within the energy level, they go in this order, S, P, D, and F. But we know that some of these sublevels, like P and D, have more than one orbital. Remember, there's more than one house on P Street. But each orbital in a sublevel is equal in energy. So each of the houses on P Street are exactly the same, so it doesn't matter which house on P Street fills up first. Rule number two is called the Pauli Exclusion Principle, named after this guy. We're less concerned with him and more concerned with what this rule says, which, first of all, is that there's a maximum of 2 electrons per orbital, 2 electrons per house. We knew that already. But in order to have 2 electrons in the same house, they have to have opposite spins. Electrons do spin, they rotate, kind of like our Earth rotates, and we know that all electrons have a -1 charge. So if you try to put 2 things that have a negative charge side by side, like charges, are going to repel. Electrons don't like to sit side by side, but it helps if they're spinning in opposite directions. That helps to account for the fact that they're both the same charge and they're sitting right next to each other. The way that we show that with our addresses, you've already seen before in the pictures with the houses and the streets. Remember, this is the symbol for the electron. It's a half arrow. You put one up and one down, and that's how you show that those electrons have opposite spins. Rule number 3 is called Hunds Rule. And Hunds Rule says in orbitals of equal energy, that would be like the 3 houses on P Street, 1 electron occupies each orbital before they pair up. So we're going to do a right example and a wrong example. And instead of drawing houses on the PowerPoint, we'll just use circles to represent electron houses. And we're going to take the second energy level, the P sublevel, so that's energy level 2, P Street, which has 3 houses, and we're going to put 2 electrons on P Street. And as we do that, remember, 1 electron occupies each orbital before they pair up. So here we're going to have our correct example and our incorrect example. On the correct example, We'll spread out the electrons as much as we can, one here and one here. And in the incorrect example, you'll see them both side by side. This is incorrect because there's empty spaces here. One electron will go in each orbital before they make a pair. So you spread the electrons out as much as you can before they pair up. And notice that these two have parallel spins. That means they're both pointing up. You do that because they're in different orbitals or in different houses. You only have to do one up and one down when they're in the same orbital. But this one is incorrect. Because there's empty spaces here, we should have spread those electrons out before pairing them up. However, there's a catch. There's always a catch. Some sublevels in a principal energy level may overlap with sublevels from other principal energy levels. And this has to do with the shapes that the energy levels are. If you think back to the last set of notes that we did, the d orbitals, they look like flowers. Those flower petals stick out pretty far from the nucleus. And it turns out that those flower petals stick out so far that it makes the next sphere, the next S sublevel, closer into the nucleus than the D sublevels. Some sublevels within an energy level may overlap with sublevels from other principal energy levels. This makes a change in the order of which houses or which seats will fill first, and it can be kind of tricky to remember. So there's a little trick for determining the order of orbitals from lowest energy to highest energy. In other words, I'm going to show you a trick for how you remember which energy levels get filled with electrons first and then next and so on. So the order of orbital filling. Imagine, again, the electrons are filing into the atom one by one. Where are they going to sit? The rules for how you use this, just follow the arrows. First thing you need to do, though, is draw yourself a grid on your notes. And it looks a little intimidating at first, but it's not too bad when you break it down into its pieces. Number 1 through 7, all on top of each other, those are all S's. Notice that the 2's are on the same horizontal line, 2S and 2P. The 3's are on the same horizontal line, 3S, 3P, 3D, and so on. So all the letters go in straight vertical lines, all the numbers go in straight horizontal lines. And then you determine which orbitals fill first by following the arrows that are going to come up on the screen. We know that the closest energy level to the nucleus will fill first. That's the 1S. And as we follow that arrow, it's almost like we cross it off the list. That one fills first. Then comes the 2S, then the 2P, then the 3S, then the 3P, and the 4S. And here's the first spot where things go out of order, where we wouldn't expect this order. The 4S fills before the 3D because the 3D has those flower petals that stick out from the nucleus further than the sphere of the 4S. Then 3D, 4P, 5S, 4D, 5P, 6S, 4F, 5D, 6P, 7S, 5F, 6D, 7P, 6F, 7D, and lastly 7F. Just follow the order of the arrows, almost like you're crossing things off as you go, and that's the order that those seats would fill up in. So, how can we show these things? How can we write down our addresses? There are a few different ways that you can write down your electron addresses. And one of them is to draw a picture. It's called an orbital diagram. It's very similar to the picture that we used for Hunds Rule, where we had the circles. Orbital diagrams are just a visual representation, or a picture, of electron orbital filling. And the easiest way to learn how to do it is just to do some examples. So we'll start with hydrogen. This is the simplest element. There's one electron. We know that the first energy level with its s sublevel is going to fill first. There's one orbital for an s. There's one house on S Street, so we draw one circle. Underneath it, we label what that is. First energy level, s sublevel. We have one electron to put in here, so we put in our single electron, and this is it. This is the orbital diagram for hydrogen. Next we have helium. Has two electrons. So again, we start with the 1s. This time we put two electrons in it, and they can both sit side by side as long as one's up and one is down. So this is the orbital diagram for helium. Then we have lithium. Lithium has 3 electrons. So the first two are going to go in the same energy level as we did before, 1s. And now we need another one. So look at your arrows. What comes after 1s? 2s. Again, just one circle because this is an s sublevel, and we have one electron to put in here. So these two together are the orbital diagram for lithium. We'll do one more, skip over a couple elements. Now we have carbon. Carbon has 6 electrons. So again, we start with 1s, which holds up to 2 electrons. Then we have 2s, which holds up to 2 electrons. 2 plus 2 is 4. I need 2 more to make 6. The next spot is the 2p. Remember, there are 3 houses on P Street, so we have 3 orbitals here. And we need to spread the electrons out before we pair them up. So 1, 2. And this is the orbital diagram. This whole thing here is the orbital diagram for carbon. But you can probably tell that this would get really long really quickly. So we can shorten this and make it a little bit easier by just writing down what's called an electron configuration. An electron configuration is the shorthand version of orbital diagrams, and it's almost like you take that picture and you make a list. You list all of the locations for the electrons in the atom. The format looks like this. The big number in front is the principal energy level. The letter is the sublevel, and again, that tells you the shape or the orbital type. And this little number right here that looks like an exponent, that's the number of electrons in that sublevel. And so if you were to read this out loud, to read this address, this would say 1s2. It says S2. You don't read it like a squared. It's not like algebra. So it's 1s2. First energy level, S sublevel, 2 electrons in it. So let's do some examples. Hydrogen, remember, had 1 electron. So hydrogen's configuration would be 1s1. Helium, which has 2 electrons, would be 1s2. Lithium has 3 electrons. Remember from the orbital diagram, 1s2 and 2s1. And you just run them all together like this in a list. 1s2, 2s1. See if you can do carbon. 1s2, 2s2, 2p2. And this comes straight off the picture with the circles that we had on the previous page. So this is a little bit shorter, a little bit faster than drawing circles and arrows, but you can probably see how even this would get pretty long if you were trying to do an element like gold or platinum, something that's pretty far down on the periodic table. So we can make this even shorter still by using what's called a noble gas abbreviation. Now you have to know where the noble gases are. Get your periodic table and look if you're not sure. Noble gases are on the right-hand side. There are 6 of them. They start with helium and go all the way down to radon. These noble gases have configurations that overlap or have much the same parts as some of the other elements, so that's why we can use them for abbreviations. So we'll go one more shorthand version, and we'll do that by looking at an example of neon as compared to sodium. So look at your periodic table, decide how many electrons neon has. Turns out there are 10. So let's do neon's electron configuration. Count as we list the electrons. 1s2, 2s2, 2p6. Remember, 3 houses on P Street times 2 electrons each means that it can hold up to 6. So 1s2, 2s2, 2p6. Now let's do the configuration for sodium. If you look on your periodic table, sodium has 11 electrons. 1s2, 2s2, 2p6, 3s1. And I've color-coded it here. You can see that the first 3 parts are the same as the configuration for neon. So if we wanted to do one more shorthand version, we could take these first 3 parts of sodium and substitute the symbol for neon, and we put it in brackets, and then we just add on whatever else we need. So we just tack on to the end whatever else remained. Okay, that's it for the electron rules. We've got one more picture to look at, and that's atomic stadium with electrons filling in the seats. And then we'll be ready for our last set of notes.